join, and then we will just allow them to have access. Gain access here. All right, so I'm going to start off. Well, good day, everyone, and a very warm welcome to you to our first South African Young Physicist Tournament, or SAYPT online workshop. I should say we welcome you, because there's a whole team of people that have been involved with IYPT for quite a long time. You're going to meet some of them today. And it's a real privilege to have you all here today. So a special welcome to past participants of the German Young Physicist Tournament and the International Young Physicist Tournament. It's wonderful to see familiar faces here who have helped to pave the way for this program in South Africa. Your passion, your perseverance has set a new benchmark for physics on school level in South Africa, and it's been a privilege to be part of that. To our new participants, and especially a warm welcome from all of us. You're joining a vibrant and growing community of young scientists who share deep curiosity about the universe, the world around us, and a desire to explore our world and our universe through the lens of physics. For those of you who don't know me, my name is Duffield, and I've been a science teacher for 3.5 decades, and it's been a great privilege for me to initiate the IYPT program in South Africa. I was privileged to meet someone from Germany who had been involved in the German Young Physicist Tournament about 10 years ago. I met this person, and he initiated the spark, as it were, in me to try and bring IYPT to South Africa. And since 2017, I've had the honor of accompanying and mentoring teams of talented young physicists who have represented our country at international physics tournaments across Europe in particular. And it's been deeply inspiring to see how the experience of these young people, how it's shaped their confidence, has sparked their curiosity and grown their love for science. And it's actually impacted on decisions they've made about their careers. So I'm excited that you, the new participants, are becoming part of this journey. And I definitely could never have traveled on this journey alone. It's not the work of one person. I've been privileged to be accompanied by two brilliant and passionate physicists, Dr. Alistair Douglas, who is online. He's my friend and he's my colleague, who is currently teaching at St. John's College in Johannesburg, an amazing professional physicist and a physics educator. And then Frank Smuts, who's a past participant of the German Young Physicist Tournament and who's currently a PhD student at UCT. Together, all three of us have formed the management team of Team South Africa at the IYPTs that we've attended. And I can tell you that it's an absolute privilege to work with such high caliber physicists. Now, before we get started, let's agree on a few online workshop protocols to help our session run smoothly and respectfully. Those of you who might have joined later, it is being recorded. Be aware of that, because this recording is going to be posted on our website. Please keep your microphones muted unless you are speaking. And if you'd like to ask a question or contribute, please use the raise hand feature or post your question in the chat. I, in particular, will be keeping my eye on the chat all throughout the workshop. When someone is speaking or presenting, please avoid interrupting. Everyone will have an opportunity to share their thoughts. We're going to have a Q&A session at the end. And if your connection allows, try and keep your camera on, but it's fine. If you're in your pajamas at the moment and you're busy sipping a nice coffee or hot chocolate, it's fine. The fact that you are present online is fine. But it is nice to see faces, and if possible. And most importantly, let's keep this supportive and encouraging. We want to explore ideas respectfully. Scientists do disagree, and let everyone feel that they are welcome. We want everyone to feel welcome and welcome to contribute, as long as done in a respectful way. So let's just quickly turn to the program for today. So it is flexible, but we have a basic program. So we'll begin with two past IYPT participants, Liat and Connor, who have just come back from IYPT in Sweden, and they're going to discuss the principles and practice of opposition and a bit about physics fights, these are essential aspects of IYPT, and certain of these aspects are also going to be aspects of the SAYPT finals, if you get to the finals. Then we'll look at an example of a physics fight where Rudolf, who was also at IYPT in July this year in Sweden, he will present his report, and then Connor and Liat will oppose. And this is just to give you an idea of a sort of a practical sense of how a physics fight unfolds. We are not going to have a full physics fight, but it does give you an idea of the nature of what we are working with here, and hopefully it will inspire you to go further. Then after that, we'll hear from several of our past GYPT and IYPT and HYPT. HYPT stands for the Hellenic Young Physicist Tournament, which we participated in last year. They'll share their experiences, insights, and reflections, if they want to, briefly, including what they've learned from their own journey through this unique competition. We'll then take a short break of about 10 minutes, and then we'll hand over to Frank Smuts, who's going to discuss the 8 SAYPT problems for the year. And together we'll analyze the problem statements, unpack key parameters that need to be investigated, concepts that need to be mastered, and then possible ways to approach your experimental work. I'll then review the timeline for this year's tournament, which is on our website, highlighting important milestones and preparation deadlines. After that, I'll hand over to Frank for the Q&A session, but we have Dr. Douglas and we have other past participants who can also answer, and they're welcome to answer. So raise any questions about the format and expectations. Whatever questions you have, we will deal with them. And then finally, I'll close with a few concluding comments, reflecting on what the SAYPT represents for South Africa's young scientists, what lies ahead, and just tie everything up. So once again, thank you for being here today. We're looking forward to a productive, engaging, and inspiring session with all of you, and to seeing the ideas and investigations that will emerge from this amazing new generation of South African physicists who we believe have the potential to be world-class and who can really transform the world. That's why we as physicists and educators are so passionate about this. So without any further ado, I'm going to stop talking, and I'm now going to hand over to Frank Smuts and to Declan, Declan was our IYPT captain. He's unfortunately not here today. Hand over to Connor and to Liat, and I'm going to step back, and I hope you enjoy our workshop.
Thank you, Don, for the fantastic introduction. I am Frank Smuts. I am also involved in the organizing of the South African Young Physicists Tournament. And what we are going to do now is show you the format of the competition, right? So with the South African Young Physicists Tournament, we have a set of 8 open-ended physics problems, of which you will choose one to investigate, right? It's just a couple of sentences, right? But again, over the next couple of months, you will do research on one of these topics. And then around February, you will submit a 10-minute presentation on this. And in the final round, you will do what's called a physics fight. Now, what is a physics fight? For this competition, in the final round, you will present on your topic for 10 to 12 minutes. And then you will also be expected to do opposition, right? So you don't just present on the work that you've done. You will also be expected to oppose someone else's project. You will have to analyze their work, what they've done, look for the good work that they've done, look for aspects that they can improve, and then engage in discussion, right? And we're going to see an example a mock physics fight with Rudolf presenting and Liat and Connor opposing. I would now like to hand over to Connor and Liat to discuss the opposition.
Okay, thank you very much, Frank. So yes, Liat and I will be running this portion of the workshop, focusing specifically on the opposition. You're going to get a taste of what an IYPT level report looks like from Rudolf's problem. But yeah, Liat and I, we had the privilege of competing at this year's IYPT in Sweden. And we're going to be focusing specifically on the opposition now. So Liat, if you could maybe share your screen. We have a little slideshow presentation here that we can run through. So we're going to be discussing the essence of opposition, things you want to be looking out to try and do in all of your oppositions, things you want to avoid, things you want to focus on. Opposition is generally the more difficult side of a physics fight because often you are facing off against very high level reports and having to poke holes in them, which can be very difficult at times. So just for a basic outline, we're going to run through the principles and the practice of opposition, and then we're going to give you a physics fight, a little bit of a demo as to what an opposition will look like. It's not going to be exactly what an opposition should look like, more of just an introduction to give you a brief idea of what an opposition should be, the things you want to be hitting. So simply, what is an opposition? Your job as the opponent in a physics fight is to point out all of the flaws with the reporter's presentation. So a successful opposition will need to do three things. Firstly, you need to identify the weaknesses. So this can be noting any experimental errors wherever they occur, where the experimental data doesn't meet the reporter's theory, incorrect interpretations of that theory, anything problematic with the report itself. And this is where I just want to speak a little bit about opposition etiquette, because it is a big thing when you go to IYPT. You need to make sure that when you are delivering your opposition, you are firm but respectful. So you don't want to come across as aggressive, but you want to get your point across in the most assertive yet respectful way possible, which transitions quite nicely into the second key thing for all oppositions. You need to acknowledge the strengths. So your presentation as the opponent needs to be very balanced. You need to identify what the reporter has done really well. Perhaps they have like a very thorough or well-explained theoretical model, or their experimental setup was very well constructed. When you go to IYPT, this is generally the easier side of opposition because most of the reports have a lot of strengths. But you need to make sure that you are mentioning them and you are laying them out to be charitable to the reporter. The third thing you need to make sure that you do is that you as the opponent control the narrative of the physics fight. So you need to ensure that as the opponent, you drive the discussion that's playing out, right? Skilled reporters are going to be very, very knowledgeable on their presentations. So you need to make sure that you don't let them dominate the physics fight, because if you allow them the space, they're going to take up the full physics fight and they're going to dominate you. So you need to make sure, and this is where, again, that being firm but respectful comes into play, that you need to make sure that you are driving the discussion in a way that is strategically valuable to you. And you need to make sure that you are getting your 2 cents in. You're not letting them dominate the fight by just blabbering on about their reports, because they're going to be able to do that for 12 minutes. So you need to make sure that you really get your piece in, you get your side in, and you control the narrative and the flow of the discussion. So you need to be able to show the jury that you can not only understand the problem, but you can think critically on it. Evaluate the physics that has been done, as well as any physics that may have been missed or wasn't touched by the reporter. You need to make sure that you can point that out. And finally, guide the fight in a way that's strategically beneficial to you. It's also essential that you present your own opinion throughout the fight, as the jury does mark you based on that. So you shouldn't just ask questions, but state explicitly whether you agree or disagree with the reporter's answer. You're not always going to get it right, but it is very important that you state your own opinion, because that is one of the judging criteria, as Liat will discuss later on. Finally, it's critical that you prioritize the most essential points of the report first, as your time management and prioritization of points is another factor that the jury will judge you on. So it's not going to help you if you spend 7 minutes of your 12-minute physics fight on a point that really lacks relevance. You need to be able to identify what the most important things or points of discussion in the fight are, sort of list them based on, what is the biggest problem to what is the, smallest problem, and prioritize whatever is most problematic with the report. And if you can prioritize that and bring that up first, you're going to bode very, very well in your physics fights. So I'm going to hand over to Liat now, who's going to run you through the structure of an opposition and what it should look like.
Okay. Hi, I'm Liat, and I will just be going more in depth about the structure of an opposition. So an opposition usually works in 4 parts. Firstly, you'd have to ask clarifying questions to the reporter. Then you give a report. Then you have a discussion with the reporter. And then finally, you have a reviewer who will ask you questions, and then a jury that will ask you questions. So let's just first start off with the clarifying questions. What happens here is the purpose here is to quickly clarify unclear details before preparing your reports. So you do this right after the presenter finishes. So you would about to get about 1 to 2 minutes. The thing here is the goal is not to debate or challenge yet. It's to clarify because you do not have the time to do so. The questions should be short and to the point, helping you understand their setup, their assumptions or equations before you actually write your reports. So it's in guidance to you. I find it really helpful for everyone in the team to jot down quick questions on the sticky notes, because although it's one person who is the opponent or opposing and speaking, the whole team actively works and actively gives you the questions, actively helps you with the report, as I will explain further. But it's really, really important that everyone is working and everyone is helping you. In this way, your speaker can fire efficiently when the time slot starts. So just some tips here. Yeah, ask short, focused questions. Don't argue or comment yet. And on the point of time managing, don't let the reporter speak for too long, because then you will not have enough time to ask your questions. So in a respectful manner, you should be guiding and you should be separating and allocating your time correctly so that all your questions are heard. And for us, what we did was we used sticky notes for quick firing of questions rather than taking time, because all your time matters here. The second point then is the actual report. And this is to present your own analysis of the reporter's work. So once you've gathered the information, this is your moment to speak. So you'll be taking the stage and you'll have a presentation to explain your opposition. So what you have to do first is summarize the reporter's work fairly, show that you actually understood and gave an overview of their report. Then the second thing is outline what worked well for them. So this shows objectivity. You should show your strengths, as Connor has been saying. And then you point out the weaknesses or questionable assumptions. And this is your analytical part. You are trying to pick out the flaws or the issues within the report. Finally, you should end off by listing the main points or questions you want to discuss in the next part. So think of this as setting the agenda for the discussion. What I would like to show you here is an example of the opposition report that we used. And although you don't have to use this template, there's many templates and many ways in order to make the opposition reports. Just quick note here, do not underestimate the slides, because the neater your slides are and the more easier to see and easier to understand your slides, it's much more easier for the jury to understand your report. And it's very important within the score sheet and actually understanding stuff. So here's a way to do it. First, you can have their qualitative explanation, give an overview and their strengths and weaknesses, then go on to the quantitative, the experimental setup, the results, the summary, and then you talk about your topics of discussion. So this is one way and a template of doing it. The next point then is the discussion. So the discussion, is where you invite the reporter back for a dialogue, but you must remember that you are leading it, as Connor also said. So you must use your slides to guide the flow. So you go point by point and ask questions to expose the reasoning gaps or like invite clarification within your report. Your goal here isn't to attack them, but to show that you can actually handle the scientific reasoning and guide a professional discussion, a professional opinion within their report, showcase the like issues and stuff. This is often where strong oppositions will stand out because they're not aggressive within like the reporter that they're speaking to, but they're calm, structured, and they're questioning, and they explain well, give clear questions, also lead the conversation, give their own opinions. So some tips here is that you should manage your time because you have like points that you would like to give the reporter. You must keep it structured and respectful, and as well as focusing on reasoning, not just the flaws. Showing your own opinion is also very important. So don't let only the reporter speak and you asking questions. You also are an important part of the discussion, and you should like show the jury that you're understanding the report and actually have your own opinion to give in the report. Now, this like another thing to note here is don't ask questions just to ask questions or just to like pass time, because at the end of the day, you yourself should understand the reports. And what I mean by this is that the jury can always turn the questions back to you in the last segment of the opposition. So the questions you must ask must be like clarifying questions, and you have to show that you don't understand, or you should have your own opinion. You should be asking questions because you found a flaw rather than trying to catch the reporter out, because at such a high level they do understand their work, and it should be like a good discussion rather than trying to take them at their worst or something. And then finally is the jury questions. Now, the jury questions is when the jury will step in, so the judges, and they'll ask you questions and ask questions to everyone. So the reporter, the opponent, and the reviewer. I know in the SAYPT, there won't be a reviewer, but it'll be questions. This part tests how well you actually understood the physics, not just how well you performed. So always be alert and like ready to back up your claims. It's a good idea for the whole team to be alert here again, since any of you might just need to step in with support or clarification. It is a team competition. So finally, I just want to show the score sheet and to see like how you are getting marked there. And the point here is that the questions you ask should be like, you get points for it being clear, being short, and apt, and that your opposition speech should show an understanding of the presentation, should have good topics and relevant topics, as well as prioritization. So your issue can't be the font of the slides. It should actually like be part of the physics. It should be like part of the qualitative or the quantitative aspects of the physics rather than like minor things. And then you should have your own opinions presented, and you should have good time management, as well as the discussion with the report. So the topics you raise and the prioritization, the own opinions that you present, and then how you conduct the discussion. So you shouldn't be aggressive because you do get marked bad for that. And then your answers to the jury and the reviewer's question. So just some final tips and takeaways. Just work as a team because it is very, very vital in actually giving a good opposition. The second thing is, if you want to have like better understanding on how opposition works, there's lots of like resources on YouTube to watch YouTube videos on past IYPT physics fights and see how an opposition works there. And then be clear and organized and prioritize your points, and remember your slide numbers as well, because it's very good to like be able to tell the reporter where to like which slide they should go to or what slide you need to go to in your presentation. It's just a minor thing, but it does help a lot. So that's just a good thing for an opposition. I think that's that.
Thank you, Liat. Okay, at this point, I would first want to make some clarifications and then move on to the physics fight. Right, so with the South African Young Physicists Tournament, this will work a bit differently to the IYPT. There will not be large teams. You register either as an individual or as a pair, so like you do in the ESCOM Expo. But indeed, the structure will be that you do a presentation followed by an opposition in the final round. Now, what we're going to show you is an example of a presentation that was done by Rudolf this year, right? So you'll see what a problem statement looks like. And through this practical example, you will see an example of how to address these physics problems. Right. So Rudolf, Connor, and Liat, are you ready to present?
Yes, sir. I'm ready.
Perfect. Yes. So okay. So now we're going to show you an example of a physics fight with presentation and opposition.
Okay, thank you. So my name is Rudolf van der Merwe, and I will be presenting problem 9, magnetic assist. If there's any problems with the presentation, like slides are not changing, please just unmute your mic and tell me, because there has been some difficulties in the past. Okay, so the problem statement asked us to attach 1 or 2 magnets to a non-magnetic and a non-conductive base, such that they attract a magnet suspended from a string. Investigate the motion
Hi,
of a moving
Rudolf.
magnet. Yes, sir.
Sorry, I think there's a problem with your slide presentation.
Okay.
Just check if you can move between slides.
Okay. I have moved, so I'm just going to change the presentation to my entire screen. Okay, so can you see the slides change?
Yes.
Okay, beautiful. So this is a problem statement. It just asks us to attach 1 or 2 magnets to a non-magnetic and a non-conductive base, such that they attract a magnet suspended from a string. Investigate how the motion of a moving magnet depends on the relevant parameters. So let's start with a qualitative explanation of the physics. Obviously, in a three-dimensional space, the bulb moves along the lower surface of a sphere, whose center is at the pendulum's pivot point, and whose radius is equal to the rod's length. And the 3 main properties of a pendulum's motion would be its free swing, the interaction between the bulb and the base plane magnets, as well as some damping or dispersion. This will be due to both air resistance on the bulb and the rod, but also due to internal friction in the string, which as it bends will convert some of that energy into heat energy. But modeling this in a three-dimensional space creates some unnecessary programmatic headaches. So instead, we adopted a plane view of the system, as if we are looking directly down on it. So the acceleration due to the pendulum's free swing will just be negative g times sine theta, and the dissipation is just modeled as some coefficient, which is proportional to the bulb's position, or velocity, which is the derivative of the position. So we're using the magnetic dipole model for the interaction between the baseplane magnets, and K just represents a dimensionless scaling factor, which parameterizes the strength of a magnet, and X just represents the position, and H is the height of a bulb above the baseplane. And we just calculate the height using simple trigonometry based on the XY coordinates, which you can see in the triangle on the lower right. So in our experimental setup, we decided to use a tripod design with carbon rods. And this just allows us to minimize the occlusion of a bulb as it moves around. And it also is just easy to manufacture and provides a rather strong pivot point. So we just use carbon fiber for the rods and wood for the base. I'm using PLA for the 3D prints, and we printed a release tower to control the exact release position of a bulb. And this just allows us to repeat the same initial conditions in different trial runs, which is later quite important. And then we just printed a holder for the magnet. However, we found a problem with this design. So essentially, if you look at the video, the magnet actually flips over when it passes a magnet on the base plane. And this is very hard to model, and it also makes the trial runs a bit more chaotic or less repeatable in a way. So instead, we just simplified the design by moving to a rigid rod design. Here you can see the CAD files of it, So we essentially just printed a roof which slides onto the tripod supports, and we have another cap which we printed and then glued to the rod, and we can just thread a string through there to act as a pivot point. But it was very important that we try to minimize the cross-sectional area of this design when looking from the camera's perspective. So we decided to use a tripod-like design instead of just something simpler like a pyramid, because that just allows us to see the bob when it passes beneath the pivot point, which is really important when you try to track the motion. And then we also printed a support structure for the magnet, which essentially just glues onto the rod, and then there's a separate bottle cap-like piece, which you can then screw in, and then the magnet just sits between them. So originally we wanted to use the open source Fizzlets tracker, which is an widely used tracker, which has good documentation and usually works really well. But unfortunately, we found that this didn't work in our application, because if you look at the bob, it changes its orientation and position, and it just appears different to the camera from different positions, and is also occluded sometimes, which is enough to prevent the software from actually tracking its motion. So instead, we just created our own motion tracking algorithm, which breaks the video up into a string of images, and then converts the image from an RGB color space to an hue, saturation, and a value space. And HSV is overall just easier to work with in most computer vision applications. And then we can just use a lower and upper bound for each of HS and V to set all the pixels which aren't blue to black, right? And then to find the position of a bob, we can just take the average coordinate of a non-zero pixels. And this is how it looks. And it seems to work quite well. And then we just do a coordinate conversion from a pixels to a Cartesian system with meters as units. So then we went on to determine the coefficient of dissipation in the system. So usually the equation of motion of a harmonic oscillator is just the second derivative of theta plus g of L sine theta is equal to 0. And since the friction is proportional to speed, we just add another term, which is k multiplied by theta dot, to represent dissipation. And the general solution of that equation is given below. But crucially, you can see that the angle theta decreases with, according to e to the power of half of a dissipation coefficient multiplied by time. So we then just track the motion of a free swing over a 50-second period, which produced the graph below. And if you then take the upper envelope of that graph, which essentially plots the amplitude of oscillations while ignoring the sine wave-like function of it, and then we just take the logarithm of that, and that should produce a reasonably straight line, which, according to our equation, should represent half of the dissipation coefficient. And this is how that dissipation coefficient correlates with our data in our numerical model, which seems to work quite well. So we wanted to visualize the chaos in the system. So we used our numerical model to compute the trajectory that the bob will follow when released from certain positions. And then we color that position according to the magnet over which a bob settled. And this is how it looks for 1, 2, and 3 magnet configurations. And judging by how there isn't large basins where it's a single color, except for the obvious exceptions, you can really show how sensitive the final state is to the initial conditions. But we wanted to quantify this chaos. So for that, we used the Lyapunov exponent, which essentially characterizes the rate of separation of two initially infinitesimally close trajectories. So it's just given by the equation where the divergence at time t is equal to e to the power of a Lyapunov exponent times time, and then multiplied by the initial distance between the two trajectories. So to calculate that, we recorded the position of the trajectories of a bob when released from virtually the same position, right? And then for every point in time, we can calculate the distance between those two bobs, which is what we plotted on the graph on the right. And at about 6 seconds, you can really see how the distance between them kind of explodes, which shows the final state sensitivity of the system. So if you then take the natural logarithm of that graph and calculate the gradient of that increase, you should get an approximation of the Lyapunov exponent, which we calculated to be 0.73 with a standard error of 0.02. And we then repeated this with 3 different sized magnets in a 2-magnet configuration, and also with 3 different sized magnets in a 3-magnet configuration. And then lastly, we also did the same thing with different numbers of magnets. But it is important to note that the Lyapunov exponent, which we calculated for the 1-magnet configuration, might be inaccurate in the sense that we don't calculate it in a way which allows for a negative Lyapunov exponent. So because it's released from the exact same position or like very close to each other, you can't really see it converge, only if it diverges or not. But because it's a 1-magnet configuration, we would expect different trajectories, even with a large separation value, to initially settle over that same magnet, which means it is converging, which would suggest a negative Lyapunov exponent. So we then wanted to compare this to our numerical model. So we scaled K, which represents the strength of a magnet, to fit the, well, in our numerical model, we scaled K to fit our observations for the smallest magnet. And then using that original value of K, we multiplied that with the ratio of the volumes of the different sized magnets to the original one. And this is how it goes. So I realized I haven't really showed a lot of a pendulum, so this is what it looks like. Okay. So in summary, we created a simple motion tracking algorithm which recognizes the bob based on its color, and we then calculated the dissipation coefficient, and we then tried to quantify the chaos by calculating the Lyapunov exponent. We also compared this to a numerical model, which showed reasonable correlation, and we then also tried to visualize the system's chaotic nature. And thank you for your time. Here is my references. Okay.
Thank you, Rudolf. We now hand over to Connor and Liat to do the opposition.
Okay, cool. We're just going to ask a handful of clarifying questions and then we'll get on to the opposition. We won't take too much time. It's a very lengthy presentation, but the opposition won't be longer than a few minutes, we promise. So first question, we just want to clarify what assumptions were made for your theoretical model?
Okay, in our theoretical model, we used like small angle approximation. We approximate sine of theta to be theta. And then also we assumed that the magnet is always facing the baseplane magnet, which might not be accurate always, but it seems to be a reasonable correlation.
Okay, thank you.
And yeah.
Okay, for the second question, what was the biggest cause for experimental error?
It would probably be either the release conditions or the way that we're tracking the motion. Because like, even though we're using this release tower, it sometimes adds a bit of spin onto the magnet, which could create disturbances. And also as a bob is occluded with some of the rods, the position, the center of that group of pixels shift slightly, which may make the motion tracking slightly inaccurate.
Thank you. We just want to ask very quickly, did you include gravitational torque anywhere in your calculations?
Yeah, we did. I think, not quite sure which slide, but we just calculated the acceleration, which is due to gravity, but not the torque itself, depending on what you mean with it. But.
Oh, so when switching to the rigid rod design, how do you verify that did not change the physical nature compared to like a true pendulum on a string?
So we didn't do exact comparisons with a string pendulum, and it does shift the center of gravity of the pendulum, but we did take this into account in our software or numerical model by changing the center of gravity of the pendulum. But even though it isn't using a string, it still does count as a pendulum, and we think that this does reflect the problem statement sufficiently.
And then I just want to clarify, how exactly did you determine whether your experimental data like matched your theoretical model? And were there any like concessions you had to make there?
Yeah, okay. So if I just change to the correct slide, we used this K value in our equation, right? It can be thought of to like parameterize the strength of a magnet, although it might include a few other coefficients. And we essentially just scaled this to fit the data that we saw in our numerical model, which might not be that accurate or that scientific, but we then just used this value of K and scaled that K value for the other magnets based on the ratio of the larger magnet's volume to the small magnet's volume.
Okay, and do you believe that that is like sufficient? Do you think it's accurate, or was there a bit of error that comes from that?
So there is inherently a bit of error that comes with it, because it doesn't, like, there's a bunch of other factors in K which might just be masked under or hide under the like veil of being the strength of a magnet, and it's just scaling that to fit the model might not be able to verify that our numerical model is accounting for all the factors or parameters correctly, but it does overall allow us to see how our model correlates, and especially how that changes based on the strength of a magnet relatively. But yeah, some improvement will probably be beneficial in that example.
Okay, thank you.
Okay, quickly, just what parameters did you investigate? Just like if you could list them.
Okay, so we investigated the strength of a magnet, the configuration of a magnet, as in like 3 magnets or 2 magnets or 1 magnet. Then obviously also the like with the configuration, we investigated like different release positions, as in maybe in a triangular configuration, we could release it from a vertex or an edge. So we investigated that, and we also investigated the effect of the mass of the bob on the like Gaussian system, although rather briefly.
Okay, thank you. That's all 4 questions.
All right, so at this point, the opposition has asked their questions. And what I assume they're doing now is they're completing their slides to do the opposition presentation. So let's give them 1 or 2 minutes.
Frank, can I just interject here whilst they're preparing?
Of course.
So for those of you who are new to all of this, I'm sure you will agree with me that Rudolf's presentation deals with physics and mathematics that goes way beyond the school syllabus. And this is one of the intimidating things about IYPT and SAYPT is that they're open-ended problems, and you're going to have to engage with physics concepts and mathematical concepts and techniques beyond school. But that is the one of the main reasons why we are so passionate about this, is because these kind of problems extend you beyond the normal syllabus that you would do, whether it's an IB syllabus or an IB syllabus or an NSC syllabus. And you'll hear later on that there's huge benefit in this. What I do want to say is that with the SAYPT, in our discussions that we've had, we decided that we don't necessarily expect the same level of mathematical engagement that you saw with what in Rudolf's presentation. Rudolf's presentation is an IYPT level presentation. SAYPT, our philosophy at this stage is that the focus is more on experimentation with qualitative modeling, where you explain using concepts rather than very sophisticated mathematical models. If, however, you do want to do that, then obviously that would count in your favor, because you're obviously digging and going deep into the math and the physics. But I don't want this to intimidate you. This is really a very high level presentation, and that's why we chose it, to the point where Rudolf actually presented this to Frank's research group at UCT, nonlinear dynamics research group at UCT, which comprised of physicists, applied mathematicians, professors. So, this is what we want to show you, what is possible. Each one of these problems that is part of the SAYPT set of problems has the potential for you to go this deep and this far with it. So, but yeah, we wanted to show you what the top standard is, but at the same time, I just want to clarify that this is not a math competition. This is a physics competition with primary focus on experimentation. So that's what I wanted to add. Thank you.
Okay. Can we start?
Yes, of course.
Okay. So just for an overview of the problem that the reporter gave on the magnetic assist, for the qualitative explanation, the setup is a magnetic pendulum where a magnetic bob interacts with the base magnets. The motion occurs on the surface of a sphere defined by the pendulum's length. 3 main effects were considered and 3 parameters were tested. So the release positions, the strength of the magnet, and the mass of the bob. For his quantitative explanation, the motion was simplified to 2D. He modeled the free swing by negative g of sin, damping by a linear term. The magnetic attraction treated as a dipole force, and the height of the bob was computed instead of stored as a separate variable. For the experimental setup, the setup is a magnetic pendulum where a magnetic bob interacts with the base magnets. So the motion occurs on the surface of a sphere defined by the pendulum's length. So for the design, a tripod structure was built using carbon fiber legs, a wooden base, and a 3D printed components. And his release mechanism, a release tower, controlled the bob's starting position. We need to note here we would like to question the accuracy of the release mechanisms, and within our clarifying questions, realize that it wasn't like completely accurate. On the holder design, initially a free rotating, we do think, this left with experimental error, and also the magnetic holder caused instability and flipping of the bob. So the design was changed to this rigid rod for more repeatable motion. Note here we question whether this compromises the physical realism of this problem. And we did get some answers, but we could add that in our discussion. So he used motion tracking with and had his own programmed his own like algorithm here. And he investigated, we would like to say like how precise the investigation of the orbits were, and we questioned the accuracy here. And then on results, the system displayed chaotic motion, verified by diverging trajectories. Experimental and numerical Lyapunov exponents were matched well, and patterns were formed by the final bob positions, confirming chaotic fractal-like behavior. And the rigid rod made more motion, more repeatable, but as again may have reduced the realism of a true pendulum. So for our team's opinions, the strengths here are there was a good visual representation of the phenomenon. We think that it was a good qualitative explanation. The experimental setup was very precise and structured. There was a clear visualization of the chaos, and it was a good comparison within his experiments, and simplifying the system to 2D made the mathematics trackable without losing the key behaviors. And Connor can take the weaknesses as well.
Sure. Yeah. So he mentions that there's a release mechanism used to sort of control the error around that, but we don't get like a very clear explanation of what the release mechanism looks like and why we think it's accurate. We questioned it in our clarifying questions, and he revealed that there was a little bit of error. We would like to bring this up a little bit more in the discussion and get some clarity on this. He then doesn't specify like uncertainty in measurements or how tracking inaccuracies may have influenced the Lyapunov exponent. We would like a little bit more clarification on this because we do think it's an important factor. We can bring this up in the discussion. And then lastly, we found that there was a problematic comparison of theory and experimentation with that K value. Again, we questioned this in our clarifying questions, and we think that this very well may have affected the validity of his theoretical model and the comparison to his findings. We'd like to discuss this a little bit more in the discussion. So we've just highlighted 2 points, 2 topics of discussion for this physics fight, just for the sake of time. In terms of theoretical questions, we want to question the link between the model and the experimental data. And then in terms of experimental questions, we just want to question around the release mechanism of the pendulum. We want some more clarity on that and exactly how that would have affected your setup. So I'd like to invite the reporter up for the brief discussion quickly.
Okay, thank you.
Okay, cool. So I just want to start firstly again. We questioned you about like the link between your model and your findings, and especially with that K value. Can you go back to that slide, please? If you could maybe present, Liat, you can stop presenting. If Rudolf can bring his presentation back up, please.
Okay.
Yeah, so you were explaining this when we questioned you in the clarifying questions. Can you just explain exactly how you use this again, please?
Okay, so we used our smallest magnets in our experimental model and numerical model, and we then calculated the Lyapunov exponent in our like physical setup, right? And then in our numerical model, we scaled K until the rate of divergence, i.e. the Lyapunov exponent, was the same between our numerical model and our experimental model. And because K just represents the strength of a magnet, which is directly proportional to its divergence, which is essentially just the acceleration of a magnet to one side, we do believe that this is an acceptable way of measuring it. And we then used this original value of K as the strength of our smallest magnet. And we then calculated the K for our medium and large magnets based on the increase in the volume of those magnets.
Okay, so do you think that this was the best way for you to compare your theory and your findings?
Probably not. It would be better to like calculate the acceleration of a magnet, strength of a magnet separately, but for the sake of time, we just decided to do this.
Yeah, we agree on that. I think that would have been a better way of going about it. I think you could have maybe that is a point of improvement, I think, on the report. I think your understanding of the theory is very good. I think it's explained very well, but I think for future improvements, that maybe would have been a better way to go about it. Now, I just want to chat quickly about the release mechanism of the pendulum. Can you go back to the slide where you mentioned that? Or maybe, yeah, can you explain exactly how the release mechanism, your release tower worked exactly?
Okay, so it's essentially a like 3D printed cylinder, which has these 2 kind of like loops at the end where a string can thread through. And then that string passes like over the rod or like around it and then threads through, like back through one of those loops. And then you can kind of tighten that string until the bob is exactly against that like release tower. And then when you release the string, it will just like let the rod go, which is what we use.
I see. So I think just for future improvements, a visual representation of what that looks like would be beneficial just for understanding and clarity's sake. But I also just want to ask, how do you think this would have affected the error in terms of release? Because obviously you're trying to release it from exactly the same place, but do you think it was fully accurate? Do you think there were more, it would have still had some errors in it?
Of course, it would have some amount of error. I mean, like,
of course, yes.
Yeah, when you are releasing it, because the like string wraps around the like rod, there's a very, very, very small amount of torque which it puts on the rod, which like maybe could rotate it a bit, but we didn't really observe this in our findings to make a like observable difference, and we don't really know of many better ways to do it. So
okay, I see. So you don't think there's any way of like mechanizing this? Perhaps you think that is the best way of releasing it?
I mean, I suppose there might be a better way of releasing it if you like designed a mechanical hand kind of thing, but
yeah, I can understand how experimentally that can be quite difficult and time consuming, which is that's fair enough. I do just think in future it would be better if there was some sort of visual representation of what it looks like exactly when you release it, because it would have been better for clarity's sake. Yeah, so when we asked you on the errors of your experimentation, you said the main two would be firstly potential errors in your tracking software, if I'm correct, and then secondly the release mechanism. That's just why I'm asking on it.
Yeah.
Okay. So can you explain one more time the errors that could have been potentially derived from your tracking software?
Okay, let me just try find my tracking software. So essentially, because we are using the average coordinates of the blue pixels, it means that when the bob passes below one of the rods, a part of that blue pixels will become black, right?
Mm-hmm.
And if the rod is on the left side of the bob, it means that only the like left side of it will disappear, which means that the center of the bob will shift about a quarter to the right.
Right.
Which, yeah, creates some inaccuracies.
So do you think that's avoidable? Like, for example, if the rods were, say, a transparent material, do you think then that would negate that error?
If the rods were transparent, I suppose you wouldn't have a problem of occlusion, but it would then refract and bend the light in a different way, which would produce another source of uncertainty.
I agree, but do you not think that it would be less than completely blocking out the object entirely?
Perhaps yes. Well, I don't know actually.
Yeah, I think that would be a good thing to look into in future. I think perhaps just or changing your camera setup in a way that you can have a constant like unobstructed view of the magnet itself, and then you could greatly reduce your errors in terms of the bob. I think that's pretty much everything we want to run through for time's sake. Just let me check here if we went through everything. Yeah, cool. Okay. That'll be all from my side. Thank you, Rudolf.
Thank you, Connor.
Perfect. Thank you. If you don't mind, I would like to ask one or two jury questions, just to also give an idea of what the jury does. Rudolf, do you mind resharing your presentation?
Okay.
Right. So my first question is, in your model, you assume that the magnetic field strength scales with the volume of the magnet. How could you test this experimentally?
We should probably just measure the force of like different magnets at a certain distance, like the force of attraction, which it exerts, and then just graph that relationship with volume. But we also, in our literature, we found some literature which suggests that it is, so we didn't think that that was necessary.
Okay, thank you. To the opposition, I would like to ask, you mentioned something called precession. Can you explain to me what precession is?
Sorry, when was that mentioned?
In your opposition presentation, you talk about precession motion.
So was this me or Liat? So
I think it was Liat.
oh, okay, okay.
I think I spelled position wrong.
Okay, no, so yeah, precession is a different concept. I would also like to ask Rudolf, what is precession?
Okay, so essentially when I observed precession, it's when you like release the bob with only a single magnet, and the like orbit isn't a closed orbit in a sense that it just follows the same path over and over, but that orbit which it follows kind of like curves and shifts a bit, which like creates a flower-like pattern. So I think the precession is essentially just how that orbit kind of like curves or changes with time.
Yeah, no, that yes, that's precession. That's where it doesn't form a closed orbit. And why does it not form a closed orbit?
I believe this is something to do with field strength, which varies according to 1 over the distance to the power 4, instead of with like gravity, which is 1 over the distance squared. And because of that relationship with the distance and strength, it creates some sort of property with the field. I forgot what it's called. It might be it's not curve, or like, I think it's called the curl of a field, but I'm not exactly sure why that is so.
Thank you, that's very interesting. All right, then I think at this point, let me first ask, do any of the other participants have questions about the presentation and opposition? Okay, if not, then I think we can move on.
Frank, I would like to suggest that we break for 10 minutes because we've now been going for 1 hour and 6 minutes, about an hour. If we can break for 10 minutes and just change the program ever so slightly, have a break, 10-minute break, and then when we come back, if we could ask Devin and Enzo, maybe you, just to give us just if a minute or two on each of your experiences with GYPT and IYPT and how it is impacted on you, because all of you have pursued further studies in physics and science, and then we can get stuck into the 8 problems. If we could do that, would you mind if we did that at all? If we take a 10-minute break now? All good. All right.
Sounds good.
Okay, we'll see you in 10 minutes time. Thank you very much.